It's quite fast.
You had a midterm yesterday?
Yeah.
Was easy?
No.
No.
Machine learning.
Machine learning to Anas Shaban.
Yeah.
Do you do research with?
He is my supervisor.
Oh, he said it was gonna be easy. He definitely liked us.
Yeah, he sent out an email the day before saying the midterm is easy. And the midterm was like way harder to practice midterm.
And way harder than like anything you've seen.
But learning, machine learning is a good thing to learn. Machine learning, deep learning, artificial intelligence.
Yeah.
This is the future.
I mean, who knows what I'll use it though? Probably not. I doubt I'll ever use it.
But it needs to have, I think, that strong mathematical background, linear algebra, optimization.
Totally, yeah.
Yeah.
It wasn't even the math for us. Like, it wasn't a math heavy exam. It was just a very conceptual heavy exam.
Mm.
And I think that was like, it was pretty fun.
Okay, so we will wait till 3 minutes and we start.
I assisted to that one. Like, what? Oh, the second one.
No, I'm sure. This weekend, next weekend. You guys finished the first part with it. Oh, you did? Nice. Think you guys have to do it? Was it too tough to finish? Like, how long took you in total?
I think we really did it all on our own, like, didn't really get any guidance from anybody, probably.
Wow, that's a lot for the first part. Holy shit.
I thought the first part was just like before you say that. That's what I thought.
That's not too tall.
First day back.
Okay.
Yeah, it's so funny. I like the class. Oh yeah, so hopefully I'll fix my reputation that I can't exactly. He said that in the lecture hall. And I'm like, there wasn't one student who left. There was like maybe one who left before the cutoff time.
I had one professor that gave us easy exams until the final exam. And then on the final exam, because he knew he wasn't going to see anyone after that, he gave us the final.
That was like Ian Fold, that's what in first year, that's what Ian Fold stood for. I remember his midterms were like, everyone got like in the 90s.
But I think that's the problem is that the profs sometimes, they actually don't realize that the exam is hard.
Like I
know.
Dr. Shabbat actually did think it was an easy.
Oh, for
midterm,
sure,
but it's like,
yeah.
oh, yeah.
He just doesn't understand that we are students.
Well, not stupid, just like limited it.
But the professor knows that if he have a tricky question,
He did have tricky questions though. Like, I would say the first question was a tricky question.
yeah,
And it's like that's my definition of like an easy exam doesn't have any tricky questions. Everything's straightforward and like, you know, if you know your stuff, you'll get it. If you don't know, you won't get it. But there's no like trick questions. Whereas hard exams have like they're trying to trick you out.
but at the end, the task of each exam is to differentiate between the different levels of students. Even if it was easy exam, okay, but I think it's not normal that all students can get the full mark.
Yeah, there
No.
should be.
Yeah.
Sure, one gets a full mark, one loses only 1 mark, and go on, even if it is easy exam, okay?
Yeah.
So we can differentiate using some tricky questions.
Yeah. I mean, like, I didn't talk to anyone who felt it.
I didn't really feel that.
I didn't feel terrible. No, I didn't either. Then I went website. Everyone was like crying.
Nah, but everyone's so dramatic. Everyone's like, the sky is falling, we all failed. Like, seriously.
So,
anymore.
Yeah.
If you go back, it's professor.
Really?
Because my brothers were students, yeah.
okay, moving on. Today we will explain the CDMA, Code Division Multiple Access. Okay, as we know, we have frequency, time, and power. These are the limited resources in the cellular networks, and we want the users to share these resources. So in CDMA, we allow all users to use the same frequency, but divide the time between users. In frequency division multiple access, we allow all users to transmit all the time, but at different frequency bands. As we have a goal, our goal is at the receiver, at the base station, the base station must be able to differentiate between or distinguish between the signal Y1, Y2, and YK if we have K users in the network. So this is our goal. In TDMA, the base station can distinguish between the received signals, as in time slot 1, we expect to receive the signal from user 1. So I can receive Y1. In time slot 2, the base station expect to receive Y2. In time slot K, the base station must receive the signal of user K. In FDMA, the signal Y1 has frequency F1. The signal Y2 has frequency F2. The signal YK has frequency FK. Okay, this is the way that we use to distinguish between different received signals at the receiver or at the base station. Actually, the problems of TDMA and FDMA, they have limited number of users can share the network resources as we divide the time. Okay, until what? Until which fraction? Okay, we will divide that frequency. At first, we have limited bandwidth. So we divide the limited bandwidth. So we limit the number of users who can have access to the network or share the resources of the networks. One way to overcome this problem is by using CDMA. In CDMA, we allow all users to transmit all time and using the full bandwidth of our system. Okay, so we are all the users in cellular networks. So you are allowed to transmit your signals all the time using the full bandwidth. But how can the base station distinguish between the different received signals? As the received signal at the base station will be, this is Y, the received signal at the base station will be H of 1, X of 1, plus H of 2, X of 2, for example, if we have 2 users, okay, plus noise. So the received signal at the base station consists of the signal of user 1 plus the signal of user 2 plus noise. So how can we extract or decode x1 only and x2 only from this equation. We have only one equation. And we have two unknown parameters. Using linear algebra, using one equation, can you find the value of two unknown parameters?
No.
You need two equations at least. Okay, but this is what we have. How can the base station using the CDMA distinguish between x1 and x2? By using orthogonal codes at the users and the base stations. What is the meaning of orthogonal?
They don't enter, like, there's no overlap, they don't interfere with each other, they're dot products.
How can, in mathematical definition, what is that?
Dot product is 0.
Yes, if we multiply the two codes, will be 0. So if I multiply x1 with code s1 and multiply x2 with code s2, okay, at the receiver, this is the received signal. We want to decode x1, so the receiver will use the same codes at users. So at first it would multiply this signal by s1, okay, so s1 by s1, okay, s1 by s2 will be 0, so we will cancel this term, so we can only decode x1. After that we want to decode x2, so using the same equation we will multiply it by s2 and so on. We will do this derivation in the next slide. This is, I want to explain an example to understand more CDMA. Okay, anyone here can speak any language other than English?
One little bit of Spanish.
Spanish, French, Urdu, Arabic, German. Okay, Arabic. That's good. Okay. That's okay. So the game that we will play now is that we will say, everyone will say in different language. For example, we like to live in Kelowna because it has good weather for them. Okay, in different language. So we will say it in Spanish, German, French, Urdu, Arabic. Okay, but let's take three of us at first. So we'll take Arabic, Urdu, French. Okay, and you are the receivers. Okay, you understand only English. Yeah, don't understand Arabic. Yeah,
I'll try.
don't understand French.
No.
Urdu. Okay. The same for you. So you will, okay, so you will say in English, okay?
In English, okay.
English. I will say in Arabic, you will say in Urdu. Okay? Let's say speak at the same time. Translate this sentence. We like to live in Kelowna. That's enough. Okay. Yeah. So ready? English, Urdu, Arabic. Okay. And you understand only English. Yeah. Okay. 1, 2, 3. نحن نحب. Raise your voice. Okay. 1, 2, 3.
We like to live in
نحن
Kelowna.
نحب أن نعيش في كيلونا. Can you distinguish between our voices?
I can only hear
English.
You only can hear his voice
early on.
because you know English. Okay, this is what is done in the base station. So at first, the base station will adjust itself to know code S1, for example. So at first, the only signal that the base station can extract from all of these signals is only X1. This is what you did now. You only extract his signal, his voice only. You don't extract or decode my signal or Iman signal. Yeah, so this is what is done at the base station. At first, the base station adjusts itself to understand only S1 language. Coding is language. Okay, so S1. So the base station will be able to understand only X1. But the base station can understand S1, S2, SK, can understand Arabic, French, German, Spanish, Urdu, all of the used languages in the network. Okay, so if you can speak English and Arabic, you will be able to extract his voice and my voice at the same time.
Right.
Okay, yeah. If you can speak Arabic, English, and Urdu, so you will be able to understand his voice, and my voice at the same time. Okay, so this is the basic idea of CDMA. The used codes in the network, the base station can understand all of these codes, can know all of these codes. Okay, and based on these codes, the base station can extract or decode the signals of each user in an individual way. But each user can know one language, as what happened now. You know only English, you know only Urdu, I know only Arabic. Okay, so every user can know only one language. So we will not make interference with each other. Okay, so as I only understand Arabic, I don't care about what he said. And I also don't care about what he said, as I don't understand them. I don't understand their language. Okay, so this is the basic idea of CDMA. So let's take this example to understand more in mathematical way. We have two users. This is the base station. We have two users. Want to communicate through this base station. User 1 has signal X1. User 2 has signal X2. Okay? User 1 will use code S1 with length. The length of this code is equal to the number of users in this network. So the length of this code will equal 2, as we have two users. Okay, this is clear to you? We have two users, so we have 2. And each symbol or each bit in the transmitted signal will multiply by this code. So we will spread each bit, the one bit, to 2 bits. Okay, this is called spreading, okay, of the signal. So X1 will be multiplied by S1. X2 will be multiplied by S2, okay? And after that, we will transmit X1, S1 to the base station. And user 2 transmits X2, S2 to the base station. So the received signal at the base station is equal to, can anyone tell me? And we transmit at the same time using the same frequency. What is the received signal at the base station?
Well, X1 wouldn't actually change.
Okay, so we can say, you can say X1, S1. For that.
Okay, so then X1, S1 plus X2, S2.
Where is the path loss in the channel?
Oh, plus H or plus.
No, the signal X1, S1, okay, the power of this signal will be attenuated by propagation in the channel by factor H1. Okay, plus this is the signal of user 1. Okay, plus X2 dot S2, and this signal will be attenuated by factor H2. Okay, plus the noise in the channel and at the receiver, as the receiver or the base station consists of electronic devices, and the electronic devices produce noise. Okay, So this is the received signal at the base station. At first, okay, I remember I missed that. S1 and S2 must be orthogonal to each other. So if we multiply S1 transpose by S2, the result must equal 0. Okay, so in our example, S1 is equal 1, 1, and S2 equal 1 minus 1. Okay, okay. At first, what is our goal at the base station? Separate the signals, extract each user signal. Yeah. So what should we do? At first, the base station will multiply y, the received signal, by half S1 y. So y will be multiplied by half S1. We multiply the received signal with the used code at user 1, S1. And half is to simplify the expression. Okay. This will equal. Can anyone help me?
Sorry, I'm kind of confused. Why is the half then?
You will see when we multiply. Okay. So, okay. Can you help me? Okay. So let's try to multiply half S1 by transpose. Yeah. That thing. By S1. So we have half outside. We have 1 multiplied by 1 1. Yeah.
One negative one for S2, right? The second vector is 1 negative 1.
This 1 by 2 multiplied by 2 by 1. So we have the dimension will be 1.
Yeah, but
No, S2.
S2 should be.
No. Sorry for that. It's 1.
Okay.
So we are here. Yeah. Can anyone help me? So it will equal 1 multiplied by 1 plus 1 plus 1. So we have outside, which will be equal 1. This, okay. That's the reason that we multiply with 1. Okay. Okay. Can anyone help me to multiply half S1 by S2? So we have half 1 minus 1. They are orthogonal. 0. Let's do it to prove that it will be 0. So 1 by 1 plus 1 by minus 1 will equal 0. Okay. So return it back to here. We know that half S1 transpose by S1 is equal to 1. So here it will equal H1 X1 plus. We know that half S1 transpose multiplied by S2 is equal 0. So and the noise will be multiplied by half S1 Z. And we have our filters that can remove the noise. So this signal is approximately the same as the signals that we can have in FDMA and CDMA. Yes. The signal of user 1 only plus noise. This is what we have in TDMA. Yeah. Okay. Let's repeat the same process by multiplying y by half S2 y. So this term will equal 0, and this term will equal H2 X2 plus half S2 Z. Okay, so we can call it half S1 Z, Z1 and a half S2Z Z2. So we will have the same signal as we can receive in TDMA. This is clear to you? Clear to you? Okay. So this is the basic idea of CDMA. If we have K users, we'll repeat this process K times in order to be able to separate the K signals. Okay. Actually, yeah, as you can see here, so we can at the end extract X1 and X2 with interference free, as this signal is considered as interference to this signal, and this signal causes interference to this signal. Okay, but at the end, we were able to have interference-free signals. So at first, the received signal, this signal, this is the received signal at the base station at first. It's considered as signal which contains interference. Okay, contains interference and noise. This signal causes interference to this signal, and this signal causes interference to this signal. And we have noise by default. But at the end, we were able to separate each signal with interference free using this technique, using the orthogonal codes. Okay, so this is the basic idea of CDMA. Let's discuss the achievable rate using CDMA.
So you just have as many, like your
So-
spreading vectors, you would have, if you had 200 users, your spreading vectors would be 200 dimensions.
Yeah.
So like, does it start to just take up too much computing power? Do you have like 100,000 users? Or?
This is a good question. Actually, this will not affect the power. How we have the power of one symbol here in CDMA, we like to call bit as symbol, okay, using modulation techniques. Do you have any experience about modulations? Don't remember modulations. Okay. So at first the power of signal x1, this is the power of x1. Okay. We will multiply the x1, our transmitted signal, with code S1. And the code S1 has length or dimension expected to be larger than the length of the transmitted signal. So what will be done is to spread so this is x1 multiplied by s1. When we multiply x1, the length or dimension of x1 will be spread, yeah? But the power also will be spread over the new dimension. Okay, so this will not affect the power transmission. Okay, so here if we have, for example, power 1, here we may transmit, if we have increased the dimension by 4, so the power may be 0.25. So transmit dimension of 4 by power 0.25 is equal to 1, which is the same power of x1. So this technique is called spreading technique, CDMA. Okay, this is a good question. Okay, so here, as we can know, the rate of each user can be multiplied by, can be obtained by the total bandwidth multiplied by the vector efficiency, bits per second per hertz. But here in the TDMA, we allocate to each user fraction of time. So we multiply by fraction, okay, of time. And if DMA, we allocate to each user fraction of bandwidth. So we multiply by the fraction of bandwidth. Here we make spreading for each one symbol. We spread it to n, which is the code length. Okay, so each one bit is spread to n. So our constant here will be 1/n. Okay, this is the achievable rate by CDMA. Okay, this is clear to you? So in TDMA, what we do, we allocate fraction of time, multiply by fraction of time. If DMA, we allocate fraction of bandwidth, so we multiply by fraction of bandwidth. Here we make spreading for each one symbol, for each symbol over n block length code. So every one symbol divided by n multiplied by the bandwidth multiplied by the spectral efficiency. This is clear to you? Okay.
Wait, so what's the units for RI?
Bits per second per bits. Yeah. No, here,
Yeah.
bits per second, yeah.
Just-
Yeah, not hertz, as the bandwidth, hertz. Okay. So as a summary, to these all techniques, TDMA, FDMA, CDMA, and TDMA, signals are orthogonal in time. Each user will be allocated different time slots from all of other users. In FDMA, signals are orthogonal in frequency. Each user will be allocated separate or different frequencies. CDMA, signals are orthogonal in codes. Okay, each user will use different code. So remember, from their names, FDMA we divide frequency, as you Daniel like to say, frequency division. TDMA, time division. CDMA, code division. Okay, and we have time, frequency, code, okay, and power. Okay, when you say time division, this means that you will use the full frequency, okay, there is no code, okay, and the full power. Okay, when you say frequency division, this means that you will use the full time and the full power. Okay, when you say code division, this will mean that you will use the full time and the full frequency. So you divide one parameter and you can use the full, all the other full parameters. Okay, this is how we can allocate resources in cellular networks. Okay, the data rate, actual data rate can be calculated using the Shannon capacity equation, which can be calculated using this equation. Actually, the derivation of this equation is very long, okay, and I am sure that you will not remember it, okay, but it's very easy, okay, but it is common if you are a communication engineer. When you ask you about what is the rate of something, your equation is bandwidth log 2 1 plus signal to interference and noise ratio. Okay, this is by default. If you told me, Mahmoud, you are proposing a new scheme, it is you discover this scheme. Can you tell me what is your rate? I will use this equation. Okay, so let's apply this equation.
You didn't want to.
Look, of 2 as we are transmitting bits, 0 1s. Okay, so let's apply this. This is the general equation. let's apply this general equation to FDMA or TDMA. In FDMA, and at first, I want to explain what is the meaning of signal to interference and noise ratio. From its name, signal to interference and noise ratio is the ratio between the power of the signal and the power of the noise and interference. Okay, and this is the parameter that we use to measure the quality of the signal. How can we say that this signal has good quality? How can I say that? Okay, but in practical, we must have noise. Little noise. And how we can say little noise? So if we have little noise and little signal power, will the signal will have good quality? No.
Signal to noise ratio.
So I must compare the power level of the original signal, the received signal, okay, and the power level of the noise and interference signals. This is, I can say that, yeah, we have good quality or not. So based on your example, low noise. Okay, I have low noise power, but at the same time, the received signal power was very low. Low by divided by low will give you big number. Okay, so no, we must compare. That's why we use this parameter. We must compare between the signal power and the noise power. In FDMA and TDMA, this is the received signal. H of I, X of I, plus Z. Okay. Okay. What is the signal power? Okay. The signal power, I want to calculate the signal to interference and noise ratio. What is the signal power? This is the, at first, the power of X1 is the transmitted power. Okay. So I transmit by power P, for example. P of I. Each user transmit with certain power level. Okay, and with the channel propagation, okay, we have losses. We have losses by factor HI. Okay, so in order to calculate the power of this HI, it will be equal HI squared. Okay. So if you want to calculate you have signal and you want to calculate its power, you multiply H by H1 transpose, which will equal H1 squared. Okay, so this is the power of the received signal. What is the power? Do you have interference here in this signal? No. So we don't have interference. Do we have noise? We have noise. Okay, we have noise. Actually, we represent the noise in the channel with a parameter called sigma square. Sigma square has a value depending on the state of the channel. Okay, and it remains constant for some time, for the time of the transmission. Okay, so the noise in the channel, usually by using some approximation techniques, remain constant during your transmission. So if you suffer from noise as your transmission is very fast, so it's a logic that the noise that we have for your full transmission to be the same. Okay, so I know that noise can change very fast, but also at some times noise can change in slow motion, in slow time. Okay, so in most of communication models, we assume that the noise will change in slow time. Okay, to simplify our expressions. So here, this is the noise. Okay, will be represented by certain parameter sigma squared. You will be given
It's
the
not just
value.
a random, like, is it actually a random variable?
It's actually a random variable.
Like Gaussian random variable?
Yes, yeah, it is Gaussian random variable. Okay, but we assume that it will be remain constant. Okay, over all transmissions over this channel. Okay, so sigma square. But in fact, user one will use that channel for fraction of time. Okay, so the noise must be multiplied by the fraction of time. Okay, as this is the value of the noise over the full transmission, and we have the transmission is divided into time slots. Okay, so we'll use the channel for only fraction of time. Okay, so this is the signal to noise ratio in case of TDMA. In FDMA, it will be the same as this is the transmitted power. It will be the same. Okay, and alpha 1 sigma square, as we will use the signal for certain frequency. Okay, so or fraction of the frequency. So the effect of the noise will be distributed over all frequencies. But I use only fraction of the bandwidth. So multiply it by the fraction of bandwidth. And so the final log will be equal log B bandwidth log 2 1 plus H1 square multiplied by B fraction of sigma square. And we also use the bandwidth for fraction of time or fraction of bandwidth. Okay, so we must multiply outside by alpha. This clear to you? In TDMA and FDMA, it will be the same. In CDMA, we spread our signal using the code spreading technique. So the bandwidth will be multiplied by n, and also the noise will be spreaded also over the new dimension n. Okay, this is the equations of how we can calculate the rate of TDMA, FDMA, CDMA. Okay, this is clear to you. Okay, so for example, I can give you, if I give you all of these parameters, you can calculate easily the rate of the FDMA, TDMA. Okay, I think this is very easy to you. Okay, so we have advanced techniques such as OFDMA and NOMA techniques. Okay, these techniques you are not required to know their operations in more details, but I will give you a hint to know these schemes. And of OFDMA, which is equal to orthogonal frequency division multiple axis, we divide the frequency and time. So each user will be given fraction of the bandwidth and the fraction of time. As you can see, for example, if I can divide the time into only 5 time slots, how many users can I serve? If I can divide my bandwidth to only 5 frequency bands, how many users can I serve? 5. If I divide the frequency and time, 5 time slots and 5 frequencies. So this will increase the number of users that can be served in the network at the same time. So you can see in TDMA, you can serve only 5, but at the same time using OFDMA, you can serve 25.
When you have like really low quality,
This will have low quality signals. Yes, if you use this sample concept, actually this is a sample concept to understand the basic idea. But we do lots of optimization here to optimize the power as the rate, as you can see, the achievable rate of each user depend on the transmitted power. Okay, if you have large transmitted power, your achievable rate will be high. Okay, so we here do lots of optimizations in terms of power to compensate the effect of allocating to you shorter time slots or frequency bands. And this is called the O of DMA. In NOMA, non-orthogonal multiple access techniques, from its name, every user can transmit using all frequencies, using all the time, using all the codes that you have, but we will distinguish between the users using their power levels. Okay, so the power allocation is one of the functions of the base station. The base stations tell every user the power level that the user will transmit. So the base station knows that, and the base station can know the channel and the bus loss of the channel. Okay, so the base station will tell Iman to transmit at power level 2, and the base station knows that power level 2 at the location of Iman, I will receive it as power level 1. Okay, the base station will tell Daniel to transmit at power level 4 because Daniel is far away. Okay, but the base station will know that Daniel will, the power received from Daniel will be received as 2, for example. Okay, the base station will tell Mahmoud to transmit at power level 7. Okay, and the base station knows that the received signal from Mahmoud will be received at power level 3. So if I receive the power level 3, this is the signal of Mahmoud. If I receive the power level 2, this is the signal of Daniel. If I receive the power signal of 1, this is the signal of Iman. Okay, so this is called NOMA, non-orthogonal multiple access. Non-orthogonal, so we don't use any orthogonal techniques. Okay, we can distinguish between different users based on their received predefined power levels. Okay, and we the base station, okay, must be sure that all the users have different power levels based on their distance. Based on your distance, the distance between the user and the base station will determine the power level allocated to you.
So if you're working on a predetermined distance, what would happen if you're in like a moving vehicle or something like if I was driving on the highway and I go from 50 kilometers away to 5 kilometers?
Yeah, actually, this is called that we have handover techniques. Okay, and in this case, your transmit signal is not affected by the distance as you are moving only. No.
But when you're using like a lot of power,
The base station can determine if the communicating user is fixed user or moving user. Okay, this is easily can be determined. As the moving user, okay, each signal consists of magnitude and phase. Okay, so if we want to present any signal, okay, we present it in magnitude and the phase of this signal. Okay, but in order to simplify our expressions, we use only the magnitude. Okay, as we speak. But in case of moving users, the phase of the signal is very important. As you are moving and you transmit a signal, and this signal, we have buildings, and the tower is here, and you are moving like this, in this way. So your signal may be reflected. You are transmit signal, yeah? Okay, and for users and base station communications, we use non-line of sight communications. You don't have to see your base station to communicate with it. As here we are in a closed room. Do you see the base station? Do you have signal in your mobile? Okay, so we're using non-line of sight, but the your signal in their in its propagation to the base station will go through many reflections, scattering. Okay, so the phase in this case is very important. So if the base station receive signal with different phases from the same user, this means that this user is moving. So based on this, the base station will have its own calculations to be able to determine to allocate to you power for each location in your move. But at certain distance, you will go out of the coverage area of this base station. The base station will communicate with the next base station that you will be associated with it and tell it, hi, base station 2, Daniel is coming to you. So be ready to receive signal from Daniel. And in mobile communications, we don't let anything to have a mistake or to have sudden situations. Sometimes we have, but when you study this field, you will discover that they don't let anything to happen without any previous plan. How can we solve this problem? No, before any standard to be launched, we must study all possible situations that can happen. So these situations happen in GSM, in 2G. Okay, handovers and the base station communicate with the other base station to tell it, oh, Daniel is moving and is coming to you, and you must be able to serve Daniel. Okay, so while you are in highways, for example, sometimes you lose the signal, or you have if you are speaking and you are moving, sometimes you feel that there is misconnection or loss of signal, and or you can't hear the voice of the one who you are communicating with. At this fraction of time, the handover with another base station is okay.
You gotta be transferring one way and swap it. It's like starting up on call. It's like that.
Yeah, but you can note this error, but most of users can. This error can't be noticed by other users. Okay, so yeah, you can see this. This is the handover. If you see this now, you must know that this is the handover error. I now will be served with another base station. Okay, so this is the process. Okay, so now you are familiar with different multiple access channels, controlled multiple access channels. They allow users to share the resources in a controlled way. Share time, share frequency, share codes, share power, for example, in a controlled way. Our goal to be able to separate signals at the base station at the end, okay, and serve as much as we can of users. But each user must have good quality of service. Based on the service that you want, each service has its own quality of service that I must provide you. Based on the quality of service, I will allocate to you the amount of power, the amount of time, the amount of frequency. Okay, so this is the overall general idea of multiple access schemes. You are required to understand FDMA, TDMA, CDMA. For OFDMA and NOMA, they are very advanced techniques to you to understand. If you want to read more about them, it's good to increase your knowledge, okay? But in this course, you are required to understand TDMA, FDMA, CDMA, okay? In the next lecture, we will go more deeper in the CDMA to understand the FDMA, okay?
Thank you.
Everything is clear to you?
Yeah.
That's good.
Have a nice weekend.
You too.